No distributed loads. Joe, you don't have your test yet, right? Okay, I have it if you want to go with me and pick it up after. All right, so who remembers what we're talking about?
Thermodynamics.
That's not remembering, that's looking in your notes.
my notebook remembers.
Formula.
Yeah. Okay, so we are doing the first law of thermodynamics for control volumes. And you want to get used to writing this so you just can come up with it eventually. I mean, I think it sort of happens naturally if you're doing these problems the way I think you should. You should just always start with the full law and then make cancellations based on what you know about the problem. So the full thing says dE dt for the control volume is equal to Q dot for the control volume minus W dot for the control volume. So far, everything looks like we're used to. And now the two big clumps of stuff that deal with the inlet and the exit. The first one, for the inlet, we have Mi dot times the quantity Hi. So that's the specific enthalpy, and that just fell together through terms, you know. It not through like a physical meaning or anything, but just through terms popping together. And then plus the speed squared at the inlet over 2. That's from the kinetic energy. Plus G times the height at the inlet. And that's that. As you can imagine, the kinetic energy term and or the potential energy term will go away a lot of times. And then we have minus all the stuff at the exit. So M exit dot times the quantity H exit plus V exit squared over 2 plus G Z E. So that's the full form before any cancellations. And here are the common cancellations to look for. The first one is steady state. So if the problem says steady state, right away you can cancel. So first, dE dt for the control volume is equal to 0. There's no change in the energy of the system over time. And second, since there's no change in the mass inside the control volume over time, we get the following thing. And this you can just always, so this is the reason, but what it turns into is that you can replace Mi dot and Me dot with just call it M dot. Okay, so there's no distinction between these two things. Okay, so if it says steady state right away, that cancels. I'm going to erase these. You probably don't want to cross these off in your notes, but that cancels. That I isn't there and that E isn't there. And that's a really common one. So these devices we're looking at, often they're going to be running steady state. I mean, usually like devices, machines, or whatever, you eventually want them to reach a steady state, or else they're going to blow up eventually. You know what I mean?
Unless that's what you're trying to do.
Blow it up. Yeah, that's true. I hadn't thought about that. You're right.
But so that would be like, it's like letting off steam exhaust or something.
Yeah, right. I mean, like heat will be going in or out, work will be going in and out, but the properties inside the volume will be steady. Okay, the second one, steady state. Okay, the second one, so what about heat transfer? So often the rate of heat transfer is going to be 0, and that is the case if any of these are true. Any single one of these will make it so you can approximate the heat transfer as 0. First, if it says that the thing is insulated, second, if it says that the device has a small surface area. Basically, you can think of all of these as like codes, that different ways of telling you that the heat transfer rate is 0. Third, if it says there's a small temperature difference between the device, the control volume, and the surroundings. Okay, so any one of those, think of that as a code that says, okay, I can cancel out that Q dot term. Third, what about the work? The rate of work done by the control volume. This is equal to 0 if all of the following things hold. Okay, so this is like a brain exercise, like SATs. So go up to number 2 again for a second, and let's write this in as, so if it's insulated, or, small surface area, or small temperature difference. Oh no, I left one out. Do you have room in your notes?
An eraser.
Okay. Will you pass it around to everybody? Okay, there's a fourth one. If it says that the fluid moves quickly, if it's a fast motion of the fluid through the device. So fast movement through the control volume. Okay, so there's 4 of those. And if any of those are true, the heat transfer is 0. And you can think about why this is, if it's insulated, insulated is designed to prevent heat transfer, so that one's sort of obvious. Heat transfer happens through the surface area, so if you make that surface area really small, then there's not much opportunity for heat to transfer. Heat transfers because of a temperature difference between the boundary and outside the boundary. So if that difference is small, then you can neglect heat transfer. And then the last one is if it doesn't have much time to transfer through the walls of the device, then there's not going to be much. So all of those sort of make sense if you think about them. And so now we're trying to figure out when the control volume doesn't do work on the surroundings, but let's see, 3 of these have to hold for that. So first is if the device is rigid. So if the device is rigid, then you can't have any, then the volume, the control volume itself doesn't change. And so there's no work of expansion. Okay. But these all have to be true. So it has to be rigid. And there can't be any rotating shafts in or out. Connected to the surroundings. And the last one, the third kind of work you can have is electrical work. So there also can't be any electrical work going in or out. We're talking about W dot. So I keep saying work, but really what we're talking about is power, the time rate of change of work. So no electrical power in or out. And then the fourth one is V squared over 2 and GZ. Those are the kinetic energy and potential energy terms. These, in most cases, have small change compared to the other terms. No, I'm sorry. This is wrong. I'm thinking of the wrong ones. What we're talking about is in the dE/dt for the control volume. The change in kinetic energy and the change in potential energy are usually small. So often what this means is that dE/dt for the control volume, we can treat that as just the time rate of change of the internal energy. Okay, so I started to write that down as if I was talking about these terms inside the parentheses, but I'm not. I'm actually talking about what's going on inside the dE/dt. Okay, any questions about those? And now I'm going to go through 5 common devices, and we're just going to go through the exercise of crossing out what we can, and we'll get kind of, it'll do 2 things. Probably the most important is just to see the exercise of how these things disappear one by one. Second, it'll give you a little bit of intuition of these devices that we're going to see all the time. Okay. So here are the common devices we'll see with their most common simplifications. But what I want you to remember is you should do these cancellations each time by yourself. And the problems won't always let all of these cancel, or sometimes they'll let more stuff cancel. So you should do the cancellations yourself each time. And so these are nozzles and diffusers. And these two are related. There are a lot of similarities between these two. They're kind of like the same device being run in the opposite direction. Third is turbines. Fourth is compressors. And fifth is pumps. And again, compressors and pumps are similar. Compressors deal with gases and pumps deal with liquids. Okay, so one by one, we're just going to go through these things. I'm going to first talk about nozzles and diffusers together. A nozzle, I'm going to try to draw this all 3D like. Ooh, that worked awesome. So the flow is this way. So this is the inlet side, and this is the exit side. And this is a nozzle. At the inlet of a nozzle, you have a high pressure and a low speed. This is the inlet side, so you can label these sub I. And then at the exit, relatively compared to the inlet, you have a low pressure at the exit and a high speed. This is like a nozzle you put on your outdoor hose, you know, to make the water spray faster. And a diffuser works the exact opposite way. So this is the inlet. This is the exit. And in this case, we have a high speed and a low pressure at the inlet. And a high pressure and a low speed at the exit. Common assumptions that we're going to make for both of these. First, we're going to assume this is steady state. Second, we're going to assume that there's no height change. From the inlet to the outlet to the exit. Third, we're going to assume that this is fast flow. And fourth, we're going to assume that this device is rigid. So let's write out the full form of the first law for control volumes and just start canceling stuff. So d dt for the control volume is equal to q dot for the control volume minus w for the control volume dot plus mi dot times the quantity hi plus vi squared over 2 plus gzi minus me dot times the quantity he plus ve squared over 2 plus gze. Steady state, what does that do? Yep, this all goes away. And it does one more thing.
Y is equal to n.
Yeah, so I'll just call these both m dot. So the whatever mass is coming in is the mass coming out, and we're just calling that the mass flow. Okay. All right, so that's steady state. Those three changes or whatever are always what happens when it says steady state. No height change from the inlet to exit. What does that change?
Just one V.
Well, since that's a difference between those two, you can, yeah, that's the right idea, but we can just cancel those out because notice that that's a change if you combine them. It wouldn't be a change if that m dot wasn't the same thing on both, but now it is. Fast flow, what does that mean?
No q dot.
Right? Make that blue. And then the last one, it's rigid. Well, you can see from my pictures that there's no rotating shafts or electrical power in or out. So this last one says W dot goes away. And so the final form says, we can write this as m dot times the quantity hi plus vi squared over 2 is equal to m dot times the quantity he plus ve squared over 2. And then you can cancel out those m dots. And we can write this, you could format this a few different ways. I guess I'll write it as hi minus he is equal to ve squared over 2 minus vi squared over 2.
V by.
That's how everyone remembers it. I'd have never heard that before, but I like that. Okay, so both nozzles and diffusers exchange enthalpy for fluid speed. The only difference is the signs of these terms, you know, the signs of the two sides. The only difference is the sign of each side of the equation. Okay, so look at these and tell me, in this form, would a nozzle have both sides positive or both sides negative?
Positive.
Yeah, right. Yeah, I just tend to think of the speeds, you know. So both sides would be positive. And then a diffuser, both sides would be negative. And so you'll get problems that mention nozzles and diffusers, but they'll throw little, you know, wrinkles at you like, okay, maybe this one has some change in height that you'd have to consider, or there is some heat exchange or whatever. And so you just have to think through and like, all you have to be able to do is go through that equation and cancel the right things and not cancel the things that don't cancel, you know. Any questions about that? I mean, that's cool. Like, look how simple that is. And that all just comes from that complicated first law for control volumes. But, you know, that's what we're going to get is kind of these very simplified forms of that messy equation. Okay, let me do an example. Let's say that steam enters a nozzle at an inlet pressure of 10 bar and an inlet temperature of 400 degrees Celsius. So don't put your, what this means is you don't want to make this nozzle with your thumb over the end. And it leaves at a pressure of 3 bar and an exit temperature of 200 degrees Celsius. If the speed is 20 meters per second at the inlet, what's the speed at the exit? And we're just going to do this with the we're just going to use this simplification from above.
In the test, you're giving us the full form, right? On that
Yeah.
equation?
That's right. Okay, so how are we going to do this? Well, I guess the connection I want you to make is anytime you see two properties at an instant, I want you to think like, okay, if we have a table of this material, we can look up anything, you know. Steam is something that we have a table for. And so I want you to look at this and say like, okay, we can look up properties. We know we're going to use this equation here. We can look up the enthalpies based on these, and that's enough to let us calculate those speeds.
So those two temperatures don't necessarily indicate a Q dot.
No, correct. I mean, remember that Q is related to energy, not temperature. Okay, so just the behavior of this fluid flow is going to change all this stuff. You know, we have a drastic difference in pressure, and so yeah, that can change all these values even without heat coming in or leaving or anything. Okay, so in the superheated steam table, we can just look up H at the inlet and H at the exit. So HI is equal to 3263.9 times 10 to the third joules per kilogram. I just looked that up in the table. And HE is 2865.5 times 10 to the third joules per kilogram. And if you're unlucky, then those are not